Welcome to The Explainer. Today we are cracking open one of the most powerful toolkits in computer science, probability and randomized algorithms. Now this isn't just going to be some dry theoretical lecture. Think of this as your secret weapon, your ultimate study guide to help you walk into that exam feeling totally prepared.
So, let's start with a question that sounds kind of weird, right? Can being random actually make you faster? I mean, we usually think of random as messy, unpredictable, inefficient. But here's the thing. In the world of computer science, randomness can be your best friend. It can unlock solutions to problems that are surprisingly elegant and lightning fast.
Okay, so here's our game plan for today. We're going to start with the absolute fundamentals. What even is probability? Then we'll get into the rules of the game for combining different events. After that, we'll dive into how you calculate averages when things are random. And then, the really fun part, algorithms that actually use guessing to be efficient. And to wrap it all up, we'll do a rapid-fire review of everything you need to know. Let's do this. First things first, we have to get a rock-solid grip on what probability actually is. Everything, and I mean everything we're going to talk about today, builds on this one core idea. So let's make sure it's crystal clear. So at its heart, probability is just a number. It's basically a scale that runs from 0 to 1. Think of it like a certainty meter, right? If the probability is 0, it means the event is completely impossible. It can't happen. If the probability is 1, it's a sure thing. It is absolutely certain to happen. And of course, most things in life fall somewhere in between. Let's make this real. Imagine a simple 6-sided die. What's the chance you roll a 4? Well, there's one 4 on there and 6 sides total, so 1 out of 6. Simple enough. What about the probability of not rolling a 6? Well, that means you could get a 1, 2, 3, 4, or 5. That's 5 different ways to succeed, so the probability is 5 out of 6. And for an even number, the winning outcomes are 2, 4, and 6, so that's 3 outcomes out of 6, which, of course, is just 1/2. Okay, dice rolls are one thing, but you know your exams, they're going to throw something way more complicated at you. So what happens when the situation gets trickier, like figuring out the odds of a poker hand? Well, it turns out we have 2 really great ways to tackle these bigger problems. So here are your 2 main strategies. Method 1, combinatorics, is all about counting. You figure out all the ways you can win, and you divide that by all the possible things that could happen. Method 2 is more like a simulation. You break the problem down into little steps, and then you multiply the chances of each step happening one after the other. Now, both methods will get you to the right answer, but depending on the problem, one is usually way easier than the other. All right, let's level up. We've got the basics down. Now we need some rules for how to combine and play with these probabilities. This is where you start to solve the really juicy problems. So, in the world of probability, you're going to hear the word event a lot. And really, all it is a fancy name for a set of outcomes we care about. So if you're rolling a die, the event the outcome is even is just the collection 2, 4, 6. It's formal language for a pretty simple idea. And just like we can add and subtract numbers, we can do things with these events. The complement is just everything that's not in your event. The union is when you get event A or event B. And the intersection is when you get A and B. Just think not, or, and. It's that simple. Okay, listen up, because this is probably the #1 mistake I see students make on exams. When you're asked for the probability of A or B, there's a huge trap waiting for you if you're not careful. And here's the trap. You forget to subtract the overlap. You can't just add the probability of A and the probability of B. Why not? Because if you do that, you've counted the things that are in both A and B twice. So you have to add P of A and P of B, and then subtract the probability of their intersection to fix it. This formula is your best friend. Don't forget it. All right, conditional probability. This concept is a real game changer. It's all about updating what we know when we get new information. The notation P of A/B literally means what's the probability of A given that we know B already happened. It's like the world just got smaller. We're no longer looking at all possibilities, just the ones inside the universe where B is true. Okay, let's move on to one of my favorite topics, and honestly, one of the most useful ideas in all of probability: expected value. This is how we can start to predict the future, kinda. So, the expected value, which we write as E of X, is basically the average you'd expect to get over the long run. And that X is just what we call a random variable, which sounds complicated, but it's just a variable whose value is determined by a random process, like the number that comes up on a die. The key here is that the expected value isn't what you'll get on any single try,
but what you'll average out to if you do it over and over and over again. This table for a die roll shows it perfectly. Look, you take each outcome, 1, 2, 3, 4, 5, 6, you multiply it by its probability, which is always 1/6, and then you just add all those up. And what do you get? 3.5. Now, of course, you can't roll a 3.5, but if you were to roll a die 1,000 times and write down all the results, the average of all those numbers would be super close to 3.5. That's what we mean by expected value. Okay, now for what I call the superpower of probability, linearity of expectation. This is your secret weapon on an exam, I'm telling you. It says that the expected value of a bunch of things added together is just the sum of their individual expected values. But here's the mind-blowing part. This works even if the variables depend on each other. This lets you take a really nasty, complicated problem and just break it down into tiny, easy-to-solve pieces. It feels like cheating, but it's pure math.
All right, enough theory. Let's get to the payoff. How do we actually use all this stuff? Well, we're going to see how probability lets us build algorithms that are so clever and so fast, all because they're not afraid to guess.
So, when it comes to randomized algorithms, there are two main flavors. First, you've got your Las Vegas algorithms. Think of a careful gambler. They will always give you the correct answer, guaranteed. The only catch is, you're not sure how long it'll take. It's usually super fast, but you might get unlucky. Then you have your Monte Carlo algorithms. These are the risk takers. They're always fast, they always finish on time. But there's a small chance their answer is wrong. So you're trading correctness for a guarantee on speed.
Quick Select is a perfect example of a Las Vegas algorithm. Let's say you have a massive unsorted list of numbers, and you need to find the 100th smallest one. Sorting the whole thing would be slow. Instead, Quick Select just picks a random number from the list, calls it the pivot, and splits the list into everything smaller and everything larger. If your pivot lands in the 100th spot, boom, you're done. If not, you know which of the two smaller lists your answer has to be in, and you just repeat the process. By picking a random pivot, you almost always slash the size of the problem in half, which makes it incredibly fast on average. Now for a Monte Carlo example that will blow your mind. Multiplying two big matrices is incredibly slow. It's what we call an O of n cubed operation, which means if you double the size of the matrices, it takes 8 times longer. Yikes. But what if you just want to check if someone else's answer is correct? With a randomized algorithm, you can do that way faster, in O of n squared time. You do this clever trick where you don't check the whole thing, you just check if the math works out for a random vector. If it doesn't, you know the answer is wrong. If it does, well, the answer is right with an incredibly high probability. You're trading absolute certainty for a massive speedup.
All right, deep breath. We have covered a ton of ground. So let's bring it all back home. We're going to wrap this up by consolidating the absolute must-know, can't-forget takeaways for your exam. This is your final cheat sheet.
Okay, screenshot this, write it down, whatever you need to do. These are the formulas you have to know. No excuses. The complement rule for figuring out the probability of not A. The union rule for A or B. And remember, don't forget to subtract the overlap. The conditional probability formula for when you get new info. The definition of expected value, your long-run average. And of course, everyone's favorite superpower, linearity of expectation. These 5 are the absolute core of what you'll need.
And that really brings us to the big final question. In a world with just insane amounts of data, with problems so complex we can barely wrap our heads around them, is a probably correct answer good enough? And the answer is absolutely, yes. Randomized algorithms show us that sometimes a ridiculously fast answer that's correct 99.999% of the time is way more valuable than a perfect answer that takes 1,000 years to compute. That trade-off, that balance between certainty and speed, that's something you'll be thinking about for your entire career.